We return to the question of regularity of extremal solutions, and we're going to start with estimates at the boundary. For this, we're going to make the assumption that omega is a bounded, smooth, and strictly convex domain. Even convex domain would be sufficient. Actually, we're going to assume that all the principal curvatures of the boundary of omega are strictly positive at any point. Anyways, under these geometric assumptions, we can prove that the extremal solution to the equation is going to be bounded in the neighborhood of the boundary. So how do we prove this? So as usual, we're going to work not with the extremal solution, but with the u lambda, lambda less than lambda star, so as to have a nice smooth function to work with. And what we're going to prove is the following estimate, that the L infinity norm of u in some neighborhood of the boundary is controlled by the L1 norm of u in all of omega. So here, omega rho is simply the set of points in omega such that the distance from x to the boundary is less than rho. And so if we prove something like this with a constant which is independent of lambda, we can of course pass to the limit as lambda goes to lambda star and conclude that u star is bounded. All right, so as I said, we're assuming that the domain has all of its principal curvatures to be strictly positive, meaning that if you take a cut of your domain in any plane, then it should look somewhat like this. Okay, so our strategy is to prove that for every fixed x on the boundary of omega, there exists a set, which I will call Ix, such that the measure of Ix is bounded below by some fixed constant gamma, which is independent of x, and u is going to be bounded above at the point x, but the value of u at any point in that set Ix. So if this is true, then we can also say that u is going to be less than the average of u over Ix, and this quantity we can bound it by 1 over gamma times the L1 norm of u. And you see, if the constant gamma is independent of x and is independent of lambda, then that's it. We've proved the L infinity estimate that we were looking for. All right, so it remains to find this set and to prove this inequality. And the way we're going to do this is by using something that we're already familiar with, which is the method of moving planes. So here's our point x naught on the boundary. Now we fix it. And here's the unit normal. Let me call it L, exterior normal at the point x naught. And what we can say is that since the curvature is strictly positive at this point in any direction, then we can find some hyperplane such that if we reflect the cap that I just drew on the paper, then its reflection stays inside of omega. So we can find lambda naught, which depends only on the geometry of the domain, such that, let's say, this set, which I should call sigma lambda. So this is a set of points in omega, which satisfies that if I move in the direction of the interior normal, then I stay between 0 and at distance 0 and lambda of x naught. So this is sigma lambda. And this hyperplane right here, as usual, we call it T lambda, and it's simply the set of points x such that the coordinate in the minus n direction of x is equal to lambda, right? And so such that for all lambda less than lambda naught, the reflection of sigma lambda through the hyperplane T lambda stays in omega. Okay, so, well, you see, if we have this, then we can proceed with the moving plane procedure exactly as we did in the case of the ball, because for this cap that I draw here, we don't know if we can use the maximum principle on thin domains, but for sure, if I take a hyperplane which is much closer to the point, then we can apply the maximum principle as usual. And the conclusion to this is that the value of u at a point x here is going to be less than the value of u at its reflection point x lambda here. And so since this is true for all the points here, that means also that at any fixed point here on the hyperplane where u and its reflection coincide, the normal derivative has the correct sign. And even by the boundary point lemma, we can say that the normal derivative in that direction is going to be strictly negative. So what we can prove by moving planes, we can prove that the normal derivative of u is going to be strictly negative in sigma lambda naught. So we have just proved the following, that the normal derivative is going to be strictly negative in some fixed cap sigma lambda naught. In the next step, what we're going to prove is something a bit stronger. That is that if we take a direction which is close to the normal, then this remains strictly negative in the following set, sigma, which is the set of points in omega, which are going to be 1/8 of lambda naught away in the minus n direction from x naught, and 3/8 of lambda naught. Okay, so this is just a perturbation argument where theta is going to belong to a neighborhood of n in the set of possible directions on the unit sphere. Okay, so the picture is the following. We have our domain here. The point x naught is here. Here is n of x naught. And we're trying to say that not only the function is going to be decreasing in this direction, but also in a whole neighborhood of directions, thetas, that I drew just here. So how do we do this? Well, we say, hey, I did the moving planes here method at this point, but I could do it also in the very same way at a point which is very close to x naught, and I could conclude that the function is going to be, again, decreasing in this theta direction all the way to some set, which would be sigma tilde, so maybe not of lambda naught, because we don't know if it's the same curvature here, but let's say in sigma tilde lambda naught over 2, that would be for sure. Okay, we can do it for this direction. We can do it for this direction. So it looks like there's going to be some region, not so far from x naught, in which the directional derivatives of u with respect to theta are going to be all strictly negative. Okay, so this is the vague idea. So let's be a little bit more precise. So we can find a neighborhood theta of n such that the theta derivative of u is negative in the set of points which are in the theta direction now at a distance lambda naught over 2 from the point x naught. So this is true because this is just applying the moving plane procedure, as I said, at any point near x naught on the boundary. And if we take this neighborhood even smaller, in fact, we can also assume that theta and n are very close to each other, And so in particular, the dot product of x minus x naught and theta minus n of x naught, we can always assume that this is less than some fixed constant. So let's say 1/8 of lambda naught, and this is true. This can be done for every x in the compact set sigma lambda naught, and for theta belonging to our neighborhood theta, which we might take smaller indeed in order to have the second inequality. All right, so now let us prove the statement, which is this one, that if we look at this region sigma, so it's some region like this, some region like this. In this region, we have the correct sign on the theta derivative of u. So, well, we say the following, that if we want to compute the coordinate of x in the minus theta direction, we can say simply that this is the same as the coordinate in the n direction plus a perturbation term, which I just wrote down. Okay, so just add and subtract n of x naught, and you get this. All right, but if you do this, then what can you say? You can say that this quantity here is going to be bounded below in norm by minus 1/8 of lambda naught. And this quantity here, x minus x naught, in turns, we know it is going to be bigger than 1/8 of lambda naught because we assume that we are in the region sigma in which this is true. So then we get that this quantity is positive, very good. And on the other side, we can say again that this quantity here, by assumption here, is less than 1/8 of lambda naught. And then minus x naught dot n of x naught, by assumption, is less than 3/8 of lambda naught. So the conclusion is that the theta coordinate, the minus theta coordinate of x, is going to be between lambda naught over 2 and 0, and this is precisely the region that was provided to us by the moving plane method applied at the near boundary point. And so we have this second step done. All right, so now the last step is to put everything together, and we're going to take rho, which is equal to lambda naught over 8, where lambda naught is the one that we've just computed. And then we fix a point x, which is going to be in the set omega rho. Recall omega rho is the set of points which distance to the boundary is at most equal to rho. Okay, now if we're close to the boundary, so we have a point x naught here. Okay, if we take a, sorry, no point x naught here, so we have a point here which is close to the boundary, and so it's going to have a projection, a unique projection, which I will give a name, and I will call it x naught. All right, we can do this. So let x naught be the projection of x on the boundary of omega. All right, so the first thing we can say is that this point, we can push it back a little bit to a first point x1, and since we are doing this in the region where the moving plane method applied, so this was t lambda naught here, so let x1, what are we going to take? We're going to move rho away from x naught in the left direction here. And so this one is going to be in the region where the moving planes method applies. So we know that u at the point x1 is going to be bigger than u at the point x, right? Okay, this is what the first step told us, because we're moving in the n direction. But now if we're at this point, we can say also that u of x1 is going to be less again than its value, let's say, in this direction, but also in this direction and also in this direction. So it's going to be less than its value on a set here, which is precisely my set Ix. And what am I going to take? I'm going to take its height equal to rho over A. And its opening here is the neighborhood theta that we discussed. All right? And so what we have is that have also u of x1, which is at the summit of the vertex, which is less than u of y for all y in the set Ix that I just described. And that's it. We've proved the inequality, and so we have the boundary estimate.